Hello and welcome to Main Engine Cutoff. I'm Anthony Colangelo, and we've got a special edition of the show today. We've got a couple of guests with us, a really interesting topic, but we're also doing this as a video show for the first time ever, if you don't count the live shows that I did that were recorded, streamed, and archived later. I guess those count, but this is the first one in the traditional sense that we're doing as video, and we're doing it that way, number one, just to have some fun. Number two, we've got some cool visuals about the topic at hand. So we're going to be talking about autonomy in space. We've got Simone D'Amico from Stanford. We've got DJ Bush from NVIDIA and Tadros from Redwire. We're going to talk about what that means when we say autonomy in space, try to cut through some of the buzzwords that are going around in the industry right now, because I feel like everyone's talking about autonomy or AI, but they aren't really giving you a lot of good examples. So this crew's working on some interesting things. They've deployed a lot in this area in space today, and I think they're the right set of people to help us understand what is really going on in this environment. So I'm excited. It's going to be a good time talking with them all. I hope you enjoy the conversation. And if you're listening to the show, you want to check out the visuals, I've got a link in the show notes. If you're watching, welcome aboard. I hope you enjoy. All right, y'all, thanks for joining me so much on a slightly experimental version, to be honest. We don't usually do video on this particular podcast that I do, so who knows? This may be the only one ever like this, and it may be the start of a new thing, so we're gonna find out together. I'm excited. We've got a really interesting cross-section of skill sets and viewpoints and a lot of interesting crossover areas, I'm sure, as well. So to start us off, since a lot of people will be listening only, I want to make sure everyone knows whose voice is whose. So we'll start off with the least surprising voice to name, Simone D'Amico. Would you like to introduce yourself?
Yes, thank you for having me. I'm an associate professor of aeronautics and astronautics and of geophysics by courtesy, and I'm the chief science officer of EraDrive, a new company spin-off from my Stanford lab.
And we've got DJ Bush out there at NVIDIA.
Yep, thanks for having me. Excited to be here. DJ Bush, Senior Account Manager supporting our aerospace customers here at NVIDIA. And then the second hat I wear is leading our space projects across NVIDIA as well.
No news coming out of that department lately in the last week or so. I have not seen your name everywhere in the space headlines, so we'll talk about that, I'm sure. And then we've got Al from Redwire, who somehow I've never had on the show, but I feel like we've orbited each other at conferences or other Redwire guests, but how's it going?
Yeah, great. So I'm Al Tadros, CTO at Redwire, based here in Silicon Valley, and I'm a big fan of your show. So finally get to speak on your show.
Were you not? I feel like you were on at least one time. Maybe not.
We talked at a conference,
That
and
might have
maybe
been it.
we grabbed a quote or two. But anyway, in full disclosure, I have the pleasure of working with Simone in his lab, and I also have the pleasure of working with DJ and the NVIDIA team. So this is a great forum and a great group to have the discussion.
Yeah, and that's, I mean, some of the background is Omar and I were talking, and a big part of this that people already heard in the intro for sure is that, you know, there's a lot of buzzwords thrown around in the area of autonomy and AI, and people just like to say it because it sounds really good and it plays really well in headlines or press releases or whatever, but you don't often hear a lot about the specific use cases or the ways that it's being deployed today or the kind of like underlying fundamental tech that's being developed and being worked on. And in my show, I typically like to look in like the 2 to 5 year ahead range, right? Not super long distance where you're talking about all sorts of futuristic stuff, but really like practical, how is this going to change my work tomorrow? And just hearing what you guys are all involved in, I feel like there's a ton of that. But we probably should start with like what we actually mean when we say autonomy. There's different levels. There's different ways that actually plays out in the real world. Simone, that might be a good one to start off on, considering some of the examples I have pulled up here. Could you just give us an overall sense when you think about autonomy, what kinds or what definitions would you use in that instance?
Thanks for the question. This is very important, also because there is no universally agreed upon definition of autonomy, especially for spacecraft. The definition depends on the field of work. But for example, I can pull from a NASA vocabulary. And NASA defines autonomy as the degree to which a system can achieve mission objectives independently from human control. Now, this is a very general definition, and I think it's reasonable. However, academics, especially in robotics, where most of the advances in autonomy in general are happening today, refer to autonomy also as the capability to adapt to circumstances or to environmental conditions that have not been foreseen at the design stage. So this is a little bit of a more, so to say, aggressive definition of autonomy from a field that is less risk averse than what space is. If you want, I can get into a more granular definition and to the levels of spacecraft autonomy. Let me know. We can continue the discussion.
Yeah, I think, and the one thing that I thought too, as you mentioned it, is like deriving it from NASA. One of the areas I feel like NASA has talked about it the most is in the concept of operations that they have for like human Mars missions, where they always are like the crew needs to have autonomy to make decisions on the fly, and it might be a good example to use that it's like it's not robots doing it, it's not software that's doing this, but there is something about the interaction mechanism there, where there are instances that would be happening too quickly in a crewed Mars mission where mission control is irrelevant because of time delay, and there needs to be a crew level decision, right? In that case, you're subbing out software for crew. But again, like that's the longer term version of this, and that's more of like authority than autonomy. And I feel like they've used the word autonomy to say that, when I think authority might be the better. But I think it would be helpful for like a more granular breakdown, because if you're, somebody who writes software, if you put enough switch cases and if-else together, you're going to make a thing that looks autonomous to people that don't know how your software is written. But I think that's different than what we're talking about when we're looking at object classification or even large-scale constellation management. So, are both of those things on that spectrum, or is there like a line where it's like, this is the start of what I would consider autonomous?
Yeah, I can really pull from my experience. In the last 20 years, I worked on several multi-satellite missions. These are missions such as formation of satellites, swarms of satellites, or rendezvous and proximity operations, where autonomy is required in order to achieve the mission objectives. When we talk about autonomy for spacecraft, I like to focus on 3 levels of autonomy. You typically find it as numbered as 2, 3, and 4. In level 2, which is the past, which is probably the most common level of autonomy for a spacecraft, this is satellites are highly micromanaged. Orbit control maneuvers are computed on the ground and then simply uploaded to the spacecraft for basically replay. So there is a very limited reaction of the satellites to events that can be anomalies, like entering some safe modes, very basic. Now, a level 3 of autonomy, which is arising, it's emerging, and is a lot of the research we are doing at the moment. Instead, even if it's still rule-based, but it's adaptive. It's more complex in terms of the automated transitions between modes that are done on board, in terms of the coordination between the satellites, the decisions that are done at the mission level, especially for fault detection, isolation, and recovery, and collision avoidance. So these are maneuvers that are autonomously computed by the satellites on board without human intervention, all the way to level 4, which is the future. Basically, a human provide a high-level goal, and I can provide examples later. And the machine, the satellites in this case, is able to learn to determine objectives to be accomplished in order to meet that high-level goal. So we are talking really about a cognitive spacecraft, which might allow, for example, for a natural language communication with an operator, that is able to do reasoning on its own in order to achieve this high-level goal of the missions. I pause here for more discussion.
I think one aspect to that last part is that does that still it in certain ways, because of the aspects that we're working with here in orbital mechanics, has to include constraints put upon that, right? Because if you deployed a constellation of communication satellites, they may realize, hey, it would be nice, a nice 400 kilometer circular orbit, at 51-degree inclination, when humans would be like, no, let's not do that one because that's where the ISS is hanging out. So maybe keep it a little outside of the keep out sphere of the ISS. So I don't think there's a point at which we achieve like escape velocity where we're not going to apply some human constraints to the systems, even at that upper end extreme. Al's making an inquisitive face, so maybe you disagree there.
Well, first of all, this is a great topic, and it could go into lots of technical depth. And the great thing about it is now people have more and more experience with their cars having levels of autonomy, right? Whether it's lane following or car pacing or changing lanes. So people have some kind of intuition in this. But there are sections of autonomy, and I'll bring up war fighting, where you will not have the luxury of pausing and having a human, just like you wouldn't in the battlefield, always have an option of assessing where your soldiers are or where your equipment is before they make some decision. And whether you call it authority or autonomy, if you are maneuvering in space to avoid something, you might not have the luxury of waiting to say, is that new trajectory on the path of something that I'm not aware of? So you have to be able to incorporate all the constraints, all the important constraints, and the flexible constraints on board, and make that part of the decision making. Now, that does not preclude us from putting in fault detection, isolation, and recovery, which we do anyway. There can be hardware failures, there can be software errors, and we still have on board some kind of decision making of, okay, there is an issue here. What is the next step in order to resolve the issue? Oftentimes, right now for space, the decision is go to safe mode, do nothing, point at the sun, and wait for a human to decide. Well, again, that isn't always feasible if you're in a combat mindset or a warfighting situation, or landing a lander on the surface of the moon. There's no time to sit and wait. So autonomy,
or even just
ideally,
a spacecraft that was weirdly designed. There's been cases I know about of like a cislunar mission where safe mode was point at the sun, but that made it so that they could not communicate with the Earth anymore, which was like, that was the wrong safe mode in that particular case.
That's right. That's right. And so the fault detection, isolation, and recovery, or FDIR, needs to protect against that. Okay, I've been looking at the sun now for a day. No one has talked to me. I need to now rotate, the other direction to say, is it possible that, they can't talk to me? So, yes, there are constraints that we have to worry about, and then there's safety concerns that we have to put in. But just like in, full self-driving cars, there are corner cases, and you mentioned the space station. Let's say the space station maneuvered, and increased its orbit. You didn't get that update, but now it's in the way. So now what do you do? Well, you need to have a backup, maybe onboard sensing that tells you, hey, there are resident space objects in the way, and that goes into part of the autonomy that says the humans aren't always right either. It isn't just AI; it's misinformation by humans or coding errors by humans, and that goes into it. So the implementation and pragmatic application of autonomy goes to that level of complexity and layers of supervision.
DJ, can we round out too? I feel like people are probably listening having some preconceived notions of why you're hanging out with us talking about this and how NVIDIA plays into it all. And maybe those are correct, maybe those are incorrect. But how does what we're talking about here come into your world and the stuff that passes by your desk every day?
Yeah, so I think, one of the keys to kind of that next level autonomy is the reasoning capabilities of these systems. And for us, that goes back to how we're training them. And so there's a lot of different areas that present challenges when you're looking to train these autonomous systems in when we look at space exploration, are largely unknown environments. And so that's how full of fidelity can we have for these different digital twin environments? So how can we, better model the lunar surface so that our perception stack can readily understand hazards and where it is, and then it can then learn to reason, okay, how do I avoid these hazards and not go into a crater or run into a boulder, things like that. So, there's a big effort on the training side of it, which is what we pulled from a lot of the work we're doing on our robotics side. And then I would say the other part of it is, in how do we enable enough compute at the edge to then host these reasoning models and these detection models, so that we're not having to downlink large data sets. We can have insights where the data is being generated, and then we can start to actuate based upon, what we've trained upon, the new inputs that we get from the different sensors, and then move to our next step.
The first half there is interesting too. Didn't necessarily have this in the rundown, but I should have, which was a lot of the modeling and simulation that has to happen either in the development of these systems or in the testing of, once you have your idea of, all right, this is my constellation, this is the jobs I'm tasking with it, I want to run that at full fidelity. Is that kind of like where the initial NVIDIA connection to space happened before you started putting H100s up into orbit, like happened last week? Or, what is the breakdown in terms of like the space projects that come across your desk? Is it all stuff that's being deployed in space, or is it a lot of stuff that's being deployed here on the ground, either data centers or, like I said, simulation environments?
Yeah, I would say traditionally it's been more on the simulation side. We've had our GPUs in space since, 2 generations ago. Ron Thor is our latest Jetson line. We've had it since Xavier. So we do have some heritage there. I would say, but like I think where the groundbreaking work that we're doing is really on that simulation side that we're deploying. So, if we can take a small data set that we have from our existing, lunar imagery, for example, and then we can add better fidelity to that. We can make sure we improve the lighting conditions so that our sensors are, the whole goal with our robotics pipeline is that we don't want our sensors to know that they're in a simulation. And so when we go to then operate in these environments, it's a like for like. And so the large effort, I think, where the value lies is how do we safely train these autonomous systems in a high fidelity simulation, so we're not sending things up and then hoping for the best when they get there. And so a lot of the work has been around that, the physics simulation. Obviously, the physics in orbit and in the lunar surface are very different than training a robot in a factory, right? So how do we have the integration of those two, and how do we make sure the simulations are physically aware so that we can understand the orbital mechanics and how that may impact, an orbital burn, or how we need to then do different trajectories. So a heavy part of the work is on the simulation side, and that's what we call, I think the best way to capsulize is our 3 computer problem. So that's how we approach our robotics. So the first computer is just how do we train the AI and the policies of the robot. The second computer is then that validation through simulation, so a high fidelity simulation to make sure that it's operating how we want it to. And then the third is that edge deployment, so that we can then actuate and then process at the edge.
Before we dive into like each of those verticals that we're talking about, software, hardware, sensors, simulation, I want to get a kind of lay of the land of how you three would interact, either through the Stanford research that's happening, but really even on missions as well. And Al might be a good person to talk to this, since I think there's a cross integration here, right, where you're building platforms for customers that are going to make use of software and fundamental research that's happening over in Simone's world, using hardware that's coming from DJ's office. So give us a sense of the interaction and how Redwire's involved in all of that, but also maybe like, who comes first in this process? Is it pretty clear that you've got to define the mission up front and then work your way back through the stack, or is it more cyclical than that?
Yeah, great question, and you're going to make me think about what did we do and in what order here. But first of all, NVIDIA and Stanford and Redwire first didn't have a strategic business plan out from the outset, right? Stanford's been doing fundamental research in a number of areas, including AI, and NVIDIA's of course been building GPUs for gaming and other applications for decades, and developing then unique software for accelerated computing. So that all has converged, and one of the points I want to make is that Redwire is looking at it from where does AI, where does advanced accelerated computing take our space systems, our solutions, well beyond where traditional approaches, not just duplicate what we can do with traditional approaches, but takes us well beyond. And that's what we wanted to do, is say, okay, how do we take autonomy, not from an incremental step, but leapfrogging ahead. So we were working, and we're a sponsor of CSER, which is a research initiative for AI-enabled autonomy at Stanford, and we were working that element of it. We saw the capability that Omniverse and other tools have that NVIDIA has been developing for the terrestrial markets, and the question was, where can we apply that and advance it in space? And then we piece those together with our customers' requirements and our customers' vision, and we say, where can we apply these to leapfrog to the next level of civil space, of commercial capabilities, cost reductions, or war fighting? And that's where we get the real pragmatic requirements and drivers to say, where do these elements advance? And I'll just give you one example. Machine vision has been progressing for many years. Some AI capabilities right now can leapfrog dramatically what machine vision has been doing, and that's one of the areas that we're looking at to enable autonomy with Stanford as an example. Of course, compute power in space has been notoriously lagging to our frustration, and that's something that NVIDIA, and others, but NVIDIA has been real leader in demonstrating the marriage of compute with software, and that's an example of where we intersect then to bring solutions to our customers.
Yeah, since CESAR was mentioned, CESAR stands for the Center of Aerospace Autonomy Research at Stanford, that was co-founded by me and Professor Pavone. Since we pioneered AI for space applications, especially starting with the first convolutional neural networks and transformers for spacecraft navigation. Then we realized that the topic is so multidisciplinary, where you need to combine skills that are rarely available in one single person. Think about the expertise in astrodynamics you need, the expertise in machine learning and artificial intelligence. How do we make that happen? And how do we enable the broader impact of these technologies? And so we thought about the triple helix model, the model where we combine academia with industry and with government. And so CESAR was born as a place where we can work together with these entities and transfer the technology more rapidly into the actual field. And Redwire is one of our sponsors, together with Blue Origin and the government, to really try to deploy AI models in space.
When you're tackling, you sent over a ton of examples that I want to go through some of these because they're really cool visuals and I think help really understand what's happening between these, small constellation and Starling with G, not the one with the K. Always important. You guys were colliding on names there for a little bit. But there's a couple different branches of examples that you sent over. So I'm curious, is this something that up front you guys sat down and said, all right, these are the problems that we need to figure out how to solve. We need to show these different things implemented on an actual mission, or we know we need this capability. Like, what is the start of these different branches of research that you're doing?
This is a great question, because it really connects to a very long path, of my career and what I have been developing stepwise in terms of an increasing complexity in space and understanding what's possible. So, for example, in previous mission, we have seen that we can use a camera in order to navigate with respect to another satellite, but with some limitations, with heavy supervision, from the ground. Downlinking the data, working with only just one target visible in the camera. And then we realized that we can do much more, especially now that there is a proliferation of space assets, and where, if you are in low Earth orbit and you look around, you start seeing tens of resident space objects in the field of view of your camera. So this starts becoming beacons. And so how do we navigate relative to this larger number of satellites? And how can we do that autonomously on board, which is a rising need for several applications, scientific, commercial, and military. And so we conceived missions and experiments in order to increase the technology readiness level for this capability. And you mentioned Starling, which is the name of a bird species. They like to flock, and they have some quite interesting consensus capabilities when flying in flocks. And that's the origin of the name of the NASA Starling mission, where for the first time we have demonstrated the capability of a swarm to navigate not only with respect to one another, the satellites of the swarm, but also with respect to other resident space objects of the population that is out there in low Earth orbit, using only optical means. So basically, it's a new era of space flight where, thanks to the fact that space is feature-rich compared to the Voyager era where we had one satellite, Now we have thousands of them. And so we can use them as beacons, similar to a GPS system, but using light in order to navigate, in order to reason, in order to cooperate with other satellites, identify threats, etc.
Is this video that might be a good example of this, where you're kind of seeing this cross section of what's happening on the Starlink mission?
Yeah, this is one of the most advanced experiments we conducted. So on the left hand side, at the top, you see a coordinate frame, which is the origin of that coordinate frame is within a satellite of the swarm. And then you see in blue and red the trajectories that are flown by other satellites of the swarm with respect to the green dot. And then you see those dashed lines that refer to moments where the satellites exchange measurements with one another from their imagery. The imagery shown on the right, you see those videos. These are actual images collected by observers during this experiment. And at the bottom, you see that we are able to navigate determining the orbits of the observer, the orbits of the other satellites, fully autonomously using only vision navigation. And this is the first time that such a coordinated or a distributed optical navigation system is deployed in orbit.
So when you say that it's doing the sort of orbit determination, is that something that it can do totally on its own, or does it need the catalog of TLEs and some knowledge of what these things may be and where they may be, or is it purely calculating it based on knowing that it's around Earth in this particular instance?
Yeah, so in this mode that you see for this experiment, there is no a priori knowledge available for the satellites that are being observed and tracked in the field of view. So we are not using tool-line elements. We are not using extra means that are provided from the ground, except for the observer. The observer satellite has GPS available on board. And you need an anchor. At least one of the satellites needs to know its own orbit. And then through this network, they are able to navigate, with respect to one another. Now, there is another mode of operations of the system we have in orbit, which is used, however, for resident space objects which are observed just in one image, one snapshot. And this happens all the time. Because you have a satellite passing through the field of view. And in that case, in order to identify, to determine, what that satellite is, we use a space object catalog, which we upload to the satellite from the ground. And so we use that space object catalog to determine who is who. And eventually, this is a great time to show this video where we are doing this on board, at the edge. You see, when the video pauses, and there is extra information provided there. We have identified an object. This is a Venezuelan, for example, Earth observation satellite. This is a satellite from SpaceX, Starlink, that we are able to identify in the field of view. Now, this goes beyond just space domain awareness and enabling space safety and security. This is an upper stage of from Rocket Lab, or this is a Soviet Cosmos satellite. Etc. So it goes beyond space domain awareness that is done autonomously on board, but get into the capability to navigate in space without extra means, just by knowing, the a priori orbits of these beacons.
One thing I was thinking about with respect to the hardware side, DJ, is the data set size of space today is hilariously small to a lot of the other data sets that are being worked here on Earth because of, and this is one thing that always comes up with people worrying about how crowded is space and is everything going to run into each other. It's like, if you have 10,000 Volkswagens on the surface of Earth, they're not going to be that close to each other. And now get even bigger than that because you're going out in these increasing larger shells. It's busy, but it's not as busy as you think it is. So you think about the satellite catalog, it's a couple thousand active satellites, thousands of pieces of debris. But that data set is nowhere close to data sets that were being used down here on Earth for all sorts of different variety of things. So is that something that when you're working in the space area, what is that comparison like, and how does it impact decisions to be made on what hardware is appropriate or applicable to these space areas right now, and how that might change as things get busier with constellations launching, tens of thousands of more over the next couple of years?
Right. Yeah, I think most of the decision honestly comes from like power availability and then how much compute can you support with that, right? Like I don't think the data set has typically been the decision factor. It's okay, how much compute can I get in here, and can I support all my other instrumentation while driving that power to those processors? So that's typically been it, and we've benefited from having the leading of the most tops for the lowest wattage on our Jetson line, so that we can get into these 3Us and these nanosats and really have a ton of processing power that can be at the edge. And so I don't think we've run into too many data sets that have pushed past that processing power. Now, I think when we get out of like the standard LEO example and we start getting into what that next wave of missions is going to be around persistent lunar colony and gateways and mining and resource extraction and logistics and all these things, I think as those tasks become more complex, then those data sets are going to explode. And so that's going to require a larger amount of compute. But those systems are going to be larger as well. So we're not going to be trying to do that with the 3U nanosat. So I think, the curve should generally follow each other, but we typically haven't been data set constrained. It's usually how much processing power can we get on board.
So, Simone, when you're tackling these different use cases and these different missions, when you are beginning the earliest phases of development and you're figuring out what you even need to do to accomplish the task, how does that eventually make its way towards the hardware suite that does need to be deployed in that case? Like, is that something that you're passing off to the team that might be building that satellite, or maybe say you're going to go build, something on a Redwire bus, or you're going to integrate, sensors from across the industry? Are you saying this is the bare minimum that I need to achieve the thing that I've just shown here on Earth in the demonstration of this technology, or what does that flow like to actually build out the spacecraft itself?
Yes, we follow the system engineering guidelines that have been defined by NASA. Well, actually, they date back to the Apollo program, and they are still really the golden standard if you provide, a proper interpretation to them and streamline. And so we start from the key objectives, and then we derive requirements for each of the subsystems. There are several fields of expertise that are needed there in order to get down to the selection of components for the system. Is an approach of divide and conquer, basically. And what we do is provide our expertise in that design for what aspects related to orbit design, to guidance, navigation, and control, which is crucial to all the advanced missions we are working on right now. So to give you an example, VISORS is a precise formation flying a mission that we are expected to launch at the end of next year. It's a virtual telescope made of two propulsive 6U CubeSats. These are shoe boxes that align very precisely at 40 meters distance to form a virtual telescope with a 40-meter focal length and achieve very high resolution imagery. For the application here, we are talking about the corona of the sun to understand the energy release mechanisms. And so you understand that in order to go through that system design process, we need the control expert, the astrodynamics expert, to speak the same language of the scientist that defines what are the objectives of the mission. And so from there, we need to find, the best trade-off in order to accomplish, to realize that instrument with a minimum cost, with a minimum complexity, the maximum reliability. When it comes to two shoe boxes, that are at 40-meter distances, you have a problem of safety. For example, how do we align them so precisely? We're talking about centimeter accurate relative position control in order to take that high resolution imagery while avoiding collisions between the satellites in the case of anomalies. And so we need to really close tightly in a concurrent engineering approach with all the other subsystem experts in order to design the system.
This one is a really cool
I wanted to,
go ahead, Al.
Yeah, no, I wanted to emphasize what Simone just described as part of the critical importance of modeling and simulation. these are systems that will never really be built fully to operate and test on the Earth the way that they're going to fly without good modeling and simulation capabilities, including synthetic data that for scenarios that you may never be able to record in orbit, may never get into, but need to make sure you set the accommodations for in the event that you do see them. Without that modeling and simulation capability, you really can't capture all the nuances that are going to go into the power management, the thermal management. And we've had systems that have been launched and gotten to the moon, seen a scenario that they didn't expect, and all of a sudden their lifetime is limited because they didn't realize there'd be reflections off of the side of the crater, or there be shadowing from this object and
If
so
you
forth.
made us
Those
say
kind of
what we're
things
thinking of
are
on the count of three, we would all say different lunar missions that have happened in the last 5 years, and we would all be
exactly
right.
exactly. But they're just so complex that you can model the moon, you can model the sun, you can model the radiation without having all that in a collaborative interacting environment. It's really hard to get to, well, what is it that the power levels, and what margins do we want to add to the power levels, because there are going to be degradations along the way. So what Simone is describing is some of the both complexities but the fun of engineering these systems. I mean, as a aerospace engineer, this is why we're doing it. It's a miracle in many ways that we actually get them to work at all, because of the complexity that goes into it. But there are engineering processes that he's described and tools that go into a methodical system of designing space systems.
Can you talk a little more about that on the Redwire level itself, on like how you guys are approaching that? Because just, I hear a lot of scuttlebutt from the industry, and it's a small industry where everyone knows each other. So then everyone knows what went wrong with everyone else's missions. And then I end up hearing it not from the person whose mission it was, but from someone else who was like, oh, what happened there was XYZ. Because I know, because my friend works on that thing. And there's been a bunch of examples in the last couple of years where somebody didn't fly, or they flew before they did like a full up complete system test where they were factoring in power generation with communications, and can we actually do both things at the same time, or do we have to choose one and then the other, and how does that impact the actual orbit that we're in? So what is that whole life cycle like?
So first of all, just I've been in the industry for 35 years. I went to college in aerospace engineering. My focus was guidance, navigation, and control, which, if you're familiar with what controls analysis and controls engineering does, oftentimes it's on console or very integrated into the operation of the satellite in orbit. So not only do I get to work on the design and test through my career, but I get to see the end product in operation. And you get to those points where you're saying, I wonder why it's doing that. And you designed it, you did it all, but that's so I've seen a little bit of everything in my career, and it's humbling. It's humbling that the amount of information that humans can retain and actually confidently recall and use versus the complexity of space systems. So and hence I have a huge appreciation. Even when I fly from San Francisco to DC, I have a huge appreciation for the airplane that I'm flying in and the engineering that goes into it. Well, some of what we're doing in at Redwire, because of that appreciation, and I give kudos to our CEO, who is the biggest champion of this, is a very strategic initiative called Dempsey. It's a digital ecosystem for mission and system integration. And basically, we're taking a lot of the COTS analysis tools, the aerospace tools, a lot of the models, and integrating them into a cohesive modeling, simulation, and engineering system. And by that, the structures engineers are collaborating with thermal engineers, with the GNC engineers, and so forth. And we can actually not only render, model, and simulate before we even get to the proposal level what the space system is going to do, how it's going to operate, and we can envision and demonstrate different design reference missions or scenarios on the output. And sometimes from that we go back to our partners and customers and say, hey, look, this is the requirement that will match what your objectives are. These are the requirements. And sometimes we need to optimize this and move that. But without that cohesive, unified modeling simulation capability, you really can't get to that endpoint of, okay, how is this going to work in reality at the end? And this isn't just for full up missions. This could be for a rollout solar array that we built for the space station, or it could be for camera systems that we put on the Orion spacecraft and capture images and do things like optical navigation. So that is something that we believe very strongly in. Dempsey is the name of our digital engineering ecosystem. And with that as a foundation, we can then start to look at even multi-domain operations. So we recently acquired a UAV or UAS company called Edge Autonomy, and a lot of missions are working in atmosphere, out of atmosphere, in VLEO at the edge of the atmosphere, and start to model and simulate multi-domain operations. So that's something that we're passionate about because of the complexity that I mentioned, and something that we're investing in internally at Redwire with so far really great results from internal involvement and benefits, but also our partners and customers who see that we're doing that.
I like to really underline the importance of this aspect. I mean, there is no shortcut. And I'm not only talking about the capability to simulate through, for example, a digital twin, the system before deployment in space. But what we pursue is a hybrid digital robotic twin. The hardware has to be included in the loop in those simulations. As it was said earlier, the hardware basically is spoofed. I mean, it should not realize that it's actually not flying in space, but it's in the lab in a so-called flat sat. And sometimes due to costs, basically some corner are cut or some tests are not conducted, and these hybrid digital robotic twins that in the past were called software in the loop versus hardware in the loop, they are not basically implemented in the most comprehensive way. And for example, for the NASA Starlink mission, just to give an idea of the lessons learned, due to the let's say constraints with the launch time, due to the reduced cost of the program, we had to sacrifice some of the tests. And then what happened when we first activated the software on board? It crashed. The software simply crashed at the beginning, and then we had to investigate on the ground, basically doing those tests that we didn't have the time to do during the development. And we simply realized that the memory that was allocated to the software stack on the microprocessor was too small for certain execution paths. And so what we did was simply to allocate more memory to the application, and then all of a sudden the magic happens and everything was working seamlessly. But there are other problems like time synchronization. Maybe a stat tracker and the GPS receiver, they start providing, working on time information that depart from one another. And you need to test that on the ground. So it's not just digital twinning, but it's a digital robotic twin of the platform that is strictly needed.
Yeah, I want to add on to that. We take digital engineering not just as the modeling and simulation, but then the capture of the requirements, the capture of the risks, and the flow down into the program. It's critically important to engineering that we don't just model and simulate, but we actually then know the design requirements that we're going to work to, and how we're going to verify those requirements. And that's all part of digital engineering. And I want to give kudos to NVIDIA for what they're doing with a lot of their software, where they don't just stop at the compute, but it's amazing what they do with some industries in the modeling of whole factories, of whole things that you couldn't even conceive of starting to analyze without this kind of capability. And then they know that they can achieve their production rate, their yield rate, and so forth. And I think NVIDIA is doing a really good job of that in other industries, and hopefully we can pull that forward into the space. And maybe DJ wants to say more to that himself.
Yeah, I think we talked about it a little bit earlier, right? If we look at autonomous space system, to us, that's a robot, and instead of doing it on Earth, we're doing it in space, right? And obviously the physics are wildly different, but that same training, validation, and deployment approach remains the same, right? So we've had a ton of innovation on the software side that enables us to do a significant amount of work on a very little amount of compute comparatively, right? And so what would not be possible on a COTS FPGA, we can host a sizable VLM at the edge that we can then use to actuate and understand and contextualize our operational environment. And I think that sim to real gap is really where that value is, right? We don't want our sensors to know that they're in a simulated environment like Simone was testing with hardware in the loop. We want them to think that they're in the real world testing, and it's expensive to test a robot on Earth and then get the real world feedback, and it's 1,000 times more expensive to do that in space. And so the more confidence that we can bring to that training cycle, the more risk that we can reduce, the more varied scenarios that we can throw at these systems, the higher level of confidence that we have to go deploy that. And that's been a huge benefit of what we've done here terrestrially. And then now we're working with our great partners like at Stanford and Redwire to then add that space layer on top of it and achieve those same outcomes.
We don't have a ton of time left, but I want to make sure we talk about some examples of what we can do with this entire stack that humans can't today. There's a lot of news of like, oh, this company's replacing all their people with LLMs or whatever, and it's like, yeah, that's not really the interesting stuff. Is like, what can you do that humans can't do yet? And I think we saw good examples earlier, Simone, of like categorizing what satellites are flying by you at any moment. I don't think anyone's going to be like, that was Starlink 3057 that just went flying by your window. But those are things that a human could do if you were given sufficient amount of time, but you don't have that time, so you can't do it. And the example that you had of the visors mission, I want to make sure I pull up this video because it was this one took me a little while to like understand what I was looking at here, but I think it's a really cool example when you're showing the way that these two satellites interact as you described earlier. I don't know if you want to talk through some of what we're seeing here in this, especially in the upper left.
Yeah, you see the two dots. These are the two satellites. And we leverage the natural dynamics because we want to spend the least propellant. And so you see these relative orbits, you see these ellipses that are flown by one of the satellites that is aligning with the other spacecraft in order to form the telescope for about 10 seconds. The 10 seconds is the integration time that the detector needs in order to take that high resolution image of the sun. Now, this has to be done in a safe manner. And so they are called passive relative orbits as such that if there is a failure on the propulsion system, then the two satellites will basically cross one another with a missed distance, with a guarantee of no collision. So that's why you see this fancy relative motion between the satellites, because they align with the sun, they take the image, but if something wrong happens, then they simply move in an helicoidal motion with respect to one another, avoiding each other. That's part of the safety concept. And nobody has ever flown such a mission with CubeSats, shoeboxes, with that level of precision to obtain a resolution which is similar to the James Webb Space Telescope at 0.1 arc second, speaking about geometric resolution.
And basically making a huge focal length out of these two spacecraft next to each other. Yeah, and that's an example of like, yeah, you could do that. You could be the person flying these two CubeSats, but you wouldn't want to do everything that's involved with this. And maybe you couldn't even like actually achieve the centimeter resolution or centimeter accuracy needed there.
No, the autonomy obviously is strictly needed in order to achieve these objectives because whenever the time is critical, so maneuvers have to be executed, at the time of every minute in order to achieve the desired control accuracy. And whenever safety is critical, because you have to avoid collision, and the human operator will never be able, to react in time, will never be able to provide that control profile in order to align the formation. This is a typical example where autonomy is strictly required. Now, I'm not saying that AI is strictly required here for this mission to be successful. AI would be required to achieve a level of autonomy number 4, which means the formation will be able to realize how well the solar science data are, and then decide to change the part of the sun that is being observed, change the detector settings autonomously in order to get the most science out of it. This is a reasoning that would happen on board that only AI with the capability to process unstructured data and solve a very complex optimization problem and a non-convex optimization problem online would be able to achieve. That would be a Visor's AI boosted that could happen in the future.
Yeah, and I think that combination of those multimodal inputs is very important, right? Because once you take the human out of the loop and you introduce the latency, having that autonomy in the AI to then synthesize that and then reason what to do next with those multimodal inputs is something that is critically important as we look to reduce human presence, increase human presence in certain areas. Complex tasks are now part of the mission profile. So I think that's where that really, hey, what could we do with humans? Sure, we could send it all back and have someone analyze it and then say, okay, now go take these 5 steps. But does the mission profile allow for that to happen? Is it going to be accurate enough? Did we miss something? Are the physics correct? There's a lot of things that go into it. I think that's where the significant value of AI at the edge is.
How do you see some of these use cases? Go ahead, Al. Sorry.
No, well, I was just going to mention maybe 2 cases where AI might enable, but autonomy is critically important. Might depend on AI tools. One is something that I'm very interested in: object recognition or characterization before it's even resolved. So in space, distances are very large, as you mentioned. Very rarely do you see anything like you see in the movies, where there it is and it's right in front of you, and it's somehow flying right next to you.
Gravity was not real. Are you saying you didn't like the movie?
Yeah, okay.
She flew to the Tiangong with a fire extinguisher, I think.
That's right. No fire extinguishers going on. So the reality is most of the stuff is unresolved in space. They look like blurry dots out there, and there are AI techniques to understanding what satellites traditionally look like. They might have solar panels, they might have reflective surfaces or thrusters or antennas. But taking a trained model and looking at a set of unresolved pixels and starting to characterize it, so you can start to apply machine vision to objects in space that typically are not directly in front of you with full resolution. The other is the direction that the world is going, which is proliferation, whether in space or air, and it's really, really hard. It might be possible for a human or a set of humans to operate 1,000 satellites even, but to operate 1,000 dynamic satellites where they're maneuvering and so forth, and understanding the realm of the ultimate objective, the condition of each satellite, because regardless of your manufacturing process, they all turn out different, just like kids. So that is a task for the modeling, simulation, and training tools that AI brings forward. So I think those 2 realms are things that just were not possible before, that we're going to start seeing much more feasible, cost-effective also. Go ahead.
I'll show the example of the imaging. I think this is one that Simone had sent over as well, where, I don't know, this is beyond my pay grade to describe what your example is here. Simone?
Well, this is a great example because it's one of the research projects that we're doing in collaboration with Redwire and funded by Redwire, where we are using the most recent techniques, which are data driven. So you can, they fall in the era of AI, in order to recover the 3D model of a spacecraft from sparse imagery, and how can we accelerate that process to make it feasible on board the satellite. And so our new algorithms that do something similar to what Al was explaining. They provide an acceleration capability in terms of recovering a 3D model of a satellite that I want to characterize, compared instead with traditional approaches. It's one of the examples where obviously AI not just enhance what we could do in the past, but enable new capabilities, such as recovering a 3D model of an object from a single image, something that would be impossible with a classical computer vision technique. But thanks to a pre-trained AI model, it's something that can be done, similar to how you, as a human, would guess the 3D shape of that object from the image.
One thing that I was thinking of as you were describing some of these use cases, Al, is like there are a lot of use cases today that feel kind of pedestrian around Earth, that seem like simple things that humans do a lot of, but it gets more unique the farther the edge gets away, right? So like, when DJ, when you're talking about like we're going to deploy stuff at the edge, it's like, well, the edge is still within a pretty fast communication time right now when we're just talking about Earth orbit or even the moon, but maybe the autonomous humans example was not so stupid from the NASA side of things, where like you deploy a couple imaging satellites around Mars, very unstable orbits, and they need to communicate with each other and do orbit determination and figure out, okay, this one should boost up a little higher to make sure we get the imagery. Edge gets so much more important when you're 30, 40, 60 light minutes away. So is there an aspect there of the developing these capabilities and realizing that the stuff that's cool today is not going to be cool around Earth in 10 years, but it will be really cool around Mars in 10 years, even if it's the same level? Does this make any sense? Does anyone feel like this? Understand where I'm going here?
Oh,
Yeah,
absolutely.
yeah, you're pushing it out further. Yeah, no, it makes sense.
Yeah. The farther the edge is, the cooler it is, even if the use case is something that we would consider, oh, that was like 10 years ago.
Well, I'd like to chime in here because, try to wonder, how come that we are able to infer or use AI chatbots or AI models on our laptops and on our phones? Because they are thin client. And thanks to the communication infrastructure, to the network, we are able to use servers, where these very heavy, very high multi-billion neurons models that can execute. Now, we can imagine a future where this will happen in near Earth space. If you think of LEO, think of GEO, in geostationary orbit, where through, for example, data centers, which is a big topic at the moment on the news, can be those servers and satellites being able to run, these decision-making, AI models online. But when we get to the moon, when we get to Mars, when we get to the ocean of Europa, when we get to rover underwater vehicles, drones on the surface of other planets, exploring caves, exploring tunnels, forget about that. You need that edge capability.
Yeah, I would double emphasize that, and we take for granted a lot of things here. Everything is devices are connected. If anybody doubts that, just check your router. How many devices are connected to your router at home? It'll list them out, and you'll say, "No, I don't have 30 devices connected." And your toaster is talking to your router half the time. So we take that for granted, and they're computing. Our Teslas or EVs are connected and charging and conditioning the batteries and all these things that are happening. And yes, unfortunately, space has been in such an austere environment, especially if we have to land something. The mass is critically important and so forth. But I just want to remind people that there are situations here on Earth in natural disasters where connection is broken off, power is broken off. There are austere environments in, national security, where you can't assume you're going to have, communications and GPS and even human interaction and intervention, but still need to operate. Those are here in domestic and now, and it makes you really appreciate things when you have a moment, a day without space, when you have a moment at home where you can't find your phone or the router goes out and you're thinking, oh my God, how do I even map my way to, the dinner tonight? And I have no idea where that address is. So there's basic things like that we are very, very take for granted, very accustomed to. That yes, are magic. As you get farther away or separated from our infrastructure, and that is what they mean by a day without space, or that it is the human quality of life is dependent on the connectivity and the compute that is all around us.
Well, this is really cool hanging out with y'all, and hopefully people enjoy the conversation. I thought it was awesome. Really cool examples, interesting cross-section between everybody. But maybe before we head out, just like a quick around the horn, if there's something that you want to point people to, we'll go same order we started in. Simone, is there anything that you want people listening to go check out, follow along with, anything that you would point them to?
Check our website. I mean, all our projects are there. And if you are interested in any of these projects, I'm talking about slab.stanford.edu, shoot an email because, we're looking for collaborators and so that would be very, very cool to work on all these topics together.
And I've got all the links to the examples that we had in the show notes. People can go and watch them full length and then jump off from there. But DJ, how about you for NVIDIA? What should people do if they're like, man, I got to get some of that in my life?
Yeah, the two I would point to. So we just had our GTC conference a week and a half ago, and we had a lightning talk around AI for space exploration. So we had some of our great partners from Northrop and Blue Origin talking about how they're leveraging a lot of the technologies that we talked about here today. So I would go look up that talk. I think that'd be very interesting for some folks. And then we've also been a sponsor of the Frontier Development Lab out of Europe, and there's been a lot of great work that leverages our same technology there. So I would look at some of the things that have taken place there, and those are two good starting points.
Al, round us out. What's up with Redwire?
Yeah. Well, first of all, thanks for this opportunity. I think it's a great conversation. It excites me, this topic. First of all, any early careers or students, there's a lot of opportunities in the space industry. It's an exciting time. In fact, I say it is the most exciting time ever in the space industry right now. Whether you want to go to the moon, work in VLEO habitats, go to Mars, it's all happening, and it's happening now. So, I think that the other thing that I would say is Redwire has a great website. If you want to look at that, reach out to me on LinkedIn if you're really interested in a topic. So please feel free to do that. We are out at conferences all the time and would welcome that. And it is very much a relationship industry. Part of it is what Anthony is doing here and connecting people and topics. So get out and get engaged. We're mostly friendly, I think. So, people who aren't in the space industry, whether you're a lawyer, economist, GPU developer, there's a little bit of everything in the space industry. So I'd welcome all of that. And again, this is one of the many exciting topics that we have in the space industry that's going on right now, and I appreciate you covering it.
Yeah, it's been awesome. I have about 8,000 topics for each one of you that I'm probably going to email you separately and be like, can you come back and talk about this one very specific thing that we glanced over entirely today? So hour, definitely not enough time, but I appreciate it very much. And thanks again.
Awesome. Thanks for having us.
Thank you so much.
Thanks again to everyone for coming on the show. It was an awesome conversation. Really had a good time talking with them. I think we went interesting places. So I hope you enjoyed it as well. Hope you enjoyed the visuals that we had there. They're really cool examples. All those links in the show notes to the things we talk about, some of the things that we didn't, but were good reference material for building the conversation. So that's it. If you like this show, if you like what I'm doing, this is a 100% listener and viewer supported institution. mainenginecutoff.com/support is where to go to sign up and join the crew there. You can get access to Miko Headlines, which is a podcast I do every single week, running through all the stories in space that are worth keeping track of. I filter out all the news you don't need to know about, fill you in on the ones that you do need to know about. It's a great way to stay up on the news and support the show. So this show was supported by 32 executive producers who made this episode possible. Thank you so much to Eunice, Russell, Donald, Stealth Julian, Pat, Fred, David, Lee, Frank, Josh from Impulse, Steve, Joel, Joakim, Matt, Natasha Sakos, Tim Dodd, the Everyday Astronaut, Chris, Theo and Violet, Heiko, Will and Lars from Agile, Jan, Warren, the Astrogators at SEE, Ryan, Better Everyday Studios, and 4 anonymous executive producers. Thank you all so much. If you've got any questions or thoughts, hit me up, Anthony@manenginecutoff.com. I guess comment here on YouTube as well. Maybe we'll keep doing more of this. Let me know if you enjoyed this. We're trying it out. We may never do it again. We may do it all the time. Who knows? It's really up to you and me. So let me know what you think. And until next time, I'll talk to you soon.